video, we're talking confidence intervals. We'll introduce the topic, see some examples out and about. We'll kind of figure out how these things are built. We'll read what components we can pull from them and also see some examples where maybe we can make inferences or we can't make inferences based on these confidence intervals. So without further ado, here, look, confidence intervals are inferences. They're predictions. Let me show you an example. For instance, a claim might go out that they say, hey, look, an average of 2.0 hours per day is spent on social media. This is particularly in the Gen Z usage. This is from a data reportal all the way back in 2021. But you might be looking at things saying, really, how do they know exactly how much time? Did they talk to every Gen Z user? Well, the chances is probably not. And so what are some clarifying questions you could ask? You could say, what about laptops? Did they include different ways of accessing social media? We could say things like, okay, they mentioned social media. What do they even count as social media? Is, for instance, like YouTube, does that count as social media? And so there's a lot of different aspects to that 2.5 hours that maybe question, what do they really mean? There's also more at play when we talk about these confidence intervals. Let me move on to the next one to demonstrate. So here's another claim for you, if you will. Here's first claim, here's second claim. Let's read it like this. 26% of Gen Z use their smartphone 10 or more hours a day. Here's a little graphic. This is common in kind of orientation stuff where they're like, hey, we know your generation, and here's some information that we can pull. But oftentimes we see these numbers, we want to ask questions like, how accurate are these claims or these inferences? I did a little bit of work and I pulled up this reference. I'm kind of in the way of most URL, but there's another URL down here for where this data comes from. If I zoom in, maybe we can get a better picture of where this data comes from. So that inference, that claim that's being made, was actually only drawn from 1,007 Gen Z individuals. Shocking that somehow we can take that information just based off 1,000 and somehow pull it onto, well, if we know there's roughly, I think in 2020, there are 65 million Gen Z users. And so the question is, well, how can I take such a small group and apply it to such a big group? Well, there's some math, some normal distribution that we'll talk about. But one thing we should understand that this 26% actually isn't exact. In fact, there's a margin of error. You can think about that like some wiggle room. It says plus or minus 3.1%, which means this 26% is not an exact guess. In fact, really, it's like 26% minus 3.1%. It's possible, but so is 26% plus 3.1%. And so when I build out what these intervals actually are, I can subtract the 3. That'll leave me with, all right, over here, the left one is going to be 22.9%. And on the right side, that's going to leave me with 29.1%. And so these are kind of really the two extremes that are possible. And then so you might be looking at the 26 and saying, why 26? In fact, any one of these, 22.9, 29.1, are all equally likely to occur. In fact, it could equally likely be, let's say, 25%. It could be 24%. Okay, I think you get the point. Any number in between those two. And so 26, the whole reason why you pick 26, well, because it's smack dab in the middle. And so, hey, look, if they're wrong, if it turns out years later somehow they talk to all 65 million individuals, if they're wrong, hopefully they're only wrong by a little bit. There's also another point of contention here, this level of confidence that each of these intervals or each of these claims are built on. We'll talk a little bit about confidence here later, but chance to say confidence intervals, or at least the claims that are in, are all over the place. You may not always recognize them as intervals, since oftentimes a claim, 2.5 hours, 26%, are made as if they're a state of fact that this is the one number. But these confidence intervals, they always come with a little bit of a margin of error or a swing. And that's something that's important to keep in mind. So where do confidence intervals come from? I hinted earlier that it has to do with the normal distribution. Let me give you the prime example up here. For instance, in the past, when we did sampling distribution, maybe we knew information about the mean, let's say dollar amount is $45, and the standard deviation is something like $9.1. With that population information, I can say, take some probability. If I took a sample of 34 individuals, I could find the probability that the sample mean is within $2. That's plus or minus $2. We can think about that $2 like a swing. Yes. I can find that probability. In fact, it looks something like this. The probability, if I take 45 and I minus 2, that's 43. If I take 45 and I add 2, that gives me 47. This probability with this certain setup is roughly 80% or 0.8 probability. If you're wondering how to do this problem, it's actually just normal distribution with our sample normal distribution, sample mean normal distribution. Not to get too much in the weeds, but this right here, this little graph shows you exactly the picture for what this normal distribution situation looks like. I have my nice normal distribution bell-shaped curve. In fact, this is how the population information is formed. Better yet, this is actually how the sample mean is drawn. This is I have it down here, distribution of, if I can swing out of the way here, the distribution of the sample mean around the population mean mu, and it has this nice shape. One of the benefits is look, if I know how the population is organized, exhibit A, here's my graph. If I know this is the population, then if I sample from that group, maybe I just take a mark here, a couple marks here, and so on. If I get a random sample, if it is truly random, it should represent the population. So I don't necessarily need the population information if I know the distribution, if I know the shape. And just like we saw with these sampling distributions, these things are shaped the same, provided that, well, we said normal if n was greater than or equal to 30. We call that the central limit theorem. And it's with that idea, this normal distribution, this sampling distribution, that we can then do the chief task of confidence intervals, or CI for short. We can estimate the population mean. Again, pretend you don't know what it is. It's maybe not 45, I don't know. Only with the sample statistic. And again, the sample statistic, this is completely random. It depends on the sample that you get, which again, the sample is random, so that makes the sample mean random. Maybe I close my eyes, I talk to 34 individuals, and I pick up a dollar amount of 44, let's say. That $44 is completely random, but I know how it's distributed. I know it's normally distributed. And ideally, this is a good estimate for the population mean, mu, which again, for this case, I don't know. But what's friendly about these two, the sample mean and the population mean, is they should be relatively close. In fact, we'll call this population mean the target parameter. That's what we're aiming to estimate. There's really two big target parameters that I'm interested in estimating. They're written over here, the population mean, mu, and the population proportion, p. This relates to that 2.5 average that we mentioned earlier, and the 26% that we have with the Gen Z users using their phone 10 or more hours in a day. And so with these ideas, the mean and the proportions, if we know how they're shaped, normal distribution, I can get out of the way a little bit, then this is the way our graph is going to be built. And so again, the idea for confidence intervals is almost the exact same thing as the sampling distribution that we've talked about in the past. But instead of me knowing population information, like the mean is 45 and I build some probability, instead now I have sample information. And from that, I can build a confidence interval based on that best guess. The math works out a little bit differently, but that's certainly a good introduction as to what we see confidence intervals. So let me further drill down on the point and give you two more key terms. So this sample mean, this $44, is based on the sample that we draw. And it's this sample mean that we often call a point estimate. It's our best guess. We say, hey, look, ideally, it's pretty close. That's what this little wavy arrow sign means, that the sample mean is close to the population mean. Granted, they're rarely ever, in fact, they're not equal. They're not the same thing. Because again, the sample mean can change based on the different samples you're talking to, but they should be very close. But how close are they? Well, there's actually a way that we can measure that. We can put our thumb actually on exactly how much, but we should have a range of values. This range comes from that swing or that margin of error that we talked about earlier, margin of error. And there's actually a very friendly way to calculate it, especially inside of Excel, but it's this interval estimate, this range of values that we call a confidence interval. So to give you a complete picture, say we take that sample mean, $44, that point estimate that we had before, we use a little bit of math, some normal distribution stuff to find out the margin of error, or the swing, is $2. Once I have those two ingredients, I can put them together because I know that this is the middle, this is my best guess, and I have a wiggle room of $2, let's say. So then I'm pretty confident, in fact, we'll talk about the level of confidence, that the mean is somewhere inside of this interval. And in fact, we know what it actually is. We know that the actual population mean is right in between at $45. And it is inside of there, but these intervals give us a good idea, a good gauge. And that's what this picture, if I can slide it out of the way, is all about with these two values. But again, because I know that normal distribution, the sample will look like the population. Again, if our sample is accurate. If you have a bad sample, yeah, there's not much saving grace there. One thing that's important to grasp, though, with these confidence intervals is I wrote a value 42 to 46. It's no more likely to actually be in the middle, like 44, than it is to be 42. In fact, every value in there is equally likely to occur. The mean could be 42, it could be 44, it could be 46, and even if I slide out of the way, it could also be 43, and it could be anything in between. I mean, it could even be something as wild as 43.7. It can be any value in between that range. I'm just giving a window as to its smallest I can imagine it being and largest I could imagine it being. And that's what these confidence intervals tell us. Again, not perfect, but they give us a range. Certainly I know it's not going to be $50, or at least I can be fairly confident it's not. Here's some examples to show us applications or sometimes limitations of these confidence intervals. Let's say you conduct a 95% confidence interval for a school's average SAT score and compute 715 all the way from 1,103. And again, this is a average. We think their average is somewhere in there. It's a huge confidence interval. On the school's website, they advise an old parameter, or something from the past, that their entire school's SAT average is 716. Now look, they're thinking, ooh, I'd love to make this claim. I'd love to tell everybody far and wide, come to our school because our SAT average is through the roof at 1,103, or at least certainly better than 716 that it's been in the past. So the question is, can you claim that the school's average SAT score has increased? Why or why not? Well, ideally we'd like to, but maybe not. In fact, here's how I'll phrase it. Look, the new SAT average is somewhere in this interval. Again, on the low end, it could be 715. On the high end, it could be 1,103. The old mean, we know exactly what it was. Maybe they calculated, got everybody's score together, and we know it's 760. Here's where the problem comes into play. Again, I'd like to claim that it's increased, and certainly it's possible that it's increased. I mean, it's possible if the average is 1,000, but not guaranteed. In fact, look at this. This population mean is inside. 716 is possible in our interval. In fact, it's even possible that the mean is equal to 715, which would in fact be lower than what it was in the past, which would certainly not be good for this school. So unfortunately, I cannot claim that it's increased. And that's one of the issues we come with confidence intervals, is when they get very wide, it limits our inferences that we can make. We can't make that claim. Let's try the next one. You conduct a 90% confidence interval for the mean IQ score of college graduates and compute that their average is on the low end, 106.5, and on the high end, 1,017.5. The general population has a mean IQ of 100. And again, that's the way the test is set up. So that's why we'll make that assertion. Here's our question. Can you claim that, on average, college graduates have a higher IQ than the general population? Why or why not? I would encourage you to frame this the exact same way. That look, for these college students, they have an average IQ somewhere in the range, we're not sure, from either 106.5 on the low end, and on the high end, we could imagine their average being 117, versus the general population, general over here, has a mean exactly equal to 100. And so the question is, hey, look, is this group, this college graduates, do they guaranteed have a higher average than that of the general population? Well, look at this 100, and the smallest I can imagine, the smallest we can imagine the mean for the college students to be is 106.5. At least we can make that assertion with 90% confidence. And so to that end, the smallest I can imagine being is still greater. So yes, I can make that claim. Since the mean for the general population is less. Again, even at the smallest case, I can still make that assertion. And so again, confidence intervals aren't the end all to be all. It's not a one claim, one number kind of thing. We need to understand these things as an interval, a range of values. And sometimes we can make great statements like, hey, look, better IQ stuff. And sometimes, unfortunately, the interval does not bear the kind of fruit that we want to. And so we need to understand the limitations. I want to talk a little bit about that 95% confidence. What do we actually mean? This is a little bit of motivation behind these intervals. And so if you'd like to skip, you can skip ahead, and that's perfectly fine. You can just look at the next bookmark down below. But the rest of us, I think it's important that we understand that 95% confidence doesn't mean that we're literally 95% confident in our interval. It actually has a bit of meaning behind it. And so I have an illustration for you here. If you remember, we talked about this database in the past, the Youth Risk Behavior Surveillance System, where we had a huge group of students, 13,583, and we treated it like a population, like a population. And we're specifically interested in the number of days per week that students are physically active for at least 60 minutes. So we think about it like mu sub active for active hours, and specifically the average active hours. So let's consider a 95% confidence interval for the average number of days per week that students are physically active is somewhere inside of this interval. Again, low end, maybe 3.23, and on the high end, 4.27. That's, again, days in a week active. Let's say this confidence interval was drawn from a sample of 100. Again, that's 100 from this 13,583, where we got a sample mean, let's say, of 3.75, and we had a margin of error of 0.52. Well, again, one really important thing, and I'll write it down here for you, is that this sample mean is completely random. And so when we write this 95% confidence, again, doesn't mean that we're 95% confident that the mean is inside that interval. Well, kind of. It means something close. Let me give you an example. Say maybe I took 25 of these 100 samples. I would have 25 different sample means. I'd have 25 of these different things. So I'd have 25 different intervals that may contain the mean. In fact, that's what this picture, if I can slide it out of the way, illustrates. That's what this picture demonstrates. And so, for instance, here's my first interval. Let's say here's the sample mean right smack dab in the middle. And it actually does contain, there it is, my true population mean, information that normally we would not have access to. And here's my second interval, which, hey, look, I got a different sample mean, but with that margin of error, I still captured what the true population mean is. And third, fourth, and so on and so forth. But if you look, there's actually one confidence interval out of the 25 I produced that is outside, that does not contain the population mean. How unfortunate would it be if you were the person that got that confidence interval and you brought this up and you said, yep, here's my confidence interval. We're pretty sure it's in here. Well, unfortunately, 95% confident means that it's possible. In fact, out of 25 samples, there's one interval that is not going to contain the mean. And so as probability is concerned, you're hopeful that it's not you, but there's certainly a chance. That 1 out of 25 comes from, right over here, let me circle it for you, 0.95 times 25 is 24. So there are 24 good confidence intervals that we know will contain the population mean, which leaves me with, if I can slide over here, 1, the one that's highlighted, will not or does not contain the population mean. And so when we make these claims, when these confidence intervals are put forward, again, it's likely it could be anywhere in the confidence interval. For instance, for this first one, the actual population mean is somewhere larger, but for the second one, it's somewhere lower. Again, the population mean can be anywhere inside these confidence intervals, but we know that at least one out of the 25 are not going to contain the population mean, which is where, again, not to get too sidetracked, oftentimes when we build these confidence intervals, sometimes instead of taking a sample of 1,000, we'll take 10 samples of 100 random, and that'll give us a more accurate representation because then I'll actually have 10 of those confidence intervals. And then based on 10 of these, There's some math involved. It's a bit more complicated beyond what we're doing right now. But I could take those and get a good picture of what my population mean would be based on 10 samples as opposed to one big one. So confidence intervals are a game of numbers. And certainly we should understand that these intervals, again, are wild. They can be anywhere in here. In fact, there is a 5% chance that the interval that we produced is bunk, does not contain the population mean, which is meant by this 95 confidence. But again, for the layman, we can simply say we are 95% confident in our interval. Let's get down to the actual computation for what's the process for computing these confidence intervals. And I have some examples as we progress. So first and foremost, let's say we know some population information, but the whole game is I have no idea what the population mean is. How can I best approximate it? Mean equals question mark. Well, first things first, I have to gather a sample at least greater than or equal to 30. And again, it better be random. And then from that, I can compute a sample mean because again, I have my data. And it's this sample mean that provides a point estimate, a best guess for what we think the mean is close to. In order to build that interval though, I need to know my wiggle room. I need to know my plus or minus. There's actually two ingredients that go into figuring out your margin of error. The first one is your level of confidence. That level of confidence can give you this critical value. This critical value, this Z, comes from the standard normal distribution. And it's that critical value that gives you that ingredient, again, based on your level of confidence. If you're 80% confident, which is what we'll pretend for this case, or anywhere from 98% confident, and that's what this table provides. So based on the level of confidence, my critical value is what we call it is 1.282. And the second ingredient for my swing, we call it the standard error, or really it's just the standard deviation, but it's the standard deviation of the sample mean that we computed. How is that moved around? What's the spread? How wild is it? We can quantify it. In fact, for this example, it's 1.56. You can see my standard deviation and then square root of n down below. You multiply those two ingredients together, and you get roughly 2. I try to make the numbers work out nicely in that way. And so if I have those two ingredients, if I know what the point estimate is and I know what my wiggle room is, well, let's subtract and add those together and we'll get my confidence interval, 42 to 46. And this confidence interval, because of that critical value, was built at 80% confidence, which again means that there's a 20% chance that the interval I produced is completely meaningless, does not contain the mean whatsoever. But there's an 80% chance that intervals built in this way will contain the mean. Like, I'm not sure what the mean is. The mean could be 42. The mean could be 46, and anywhere in between. It could be 44.2. We're not sure. But I can tell you that it's within that interval, at least with, again, 80% confidence. So that's the logical argument that these intervals come from. Now let's see, again, some more applications for how these things are used and also how you can extract information from them. Here's our third example. A college student researching study habits collects data from a random sample of 250 college students on our campus and calculates that the sample mean is 15.7 hours per week. That's time spent studying. If the margin of error for her data is using a 90% confidence level, is E for margin of error is 0.6 hours. Construct a 90% confidence interval for her data. Interpret your results. Again, keep in mind, anytime you hear confidence interval, that's always going to be, and I'll write the more rigorous definition, then we'll get to the more friendly one, but it's always going to be your point estimate minus your margin of error, your point estimate plus your margin of error. Where again, that's always your left, your smaller point, and your right, your larger point. But instead, let me write it like this, that I have my left, my smallest point, is really just going to be X bar minus my margin of error, or E. And so I can write this out. That will be 15.7 minus 0.6, which will give me a nice number like 15.1. That's hours per week studying. That's on the low end. And again, maybe studying could be something like doing homework. Okay, it doesn't have to be literally you studying and preparing because that's a long time for a week. On the right side, the mean plus my margin of error is going to be 15.7 plus this 0.6 business. If you add those together, you'll get 16.3. And so when we're entering it in, on the low end, 15.5, and on the high end, 16.3. In fact, we could draw a little graph. That's what the graph is above me. That look on the small end, I'm thinking it's 15.1 hours. On the large end, 16.3. This is a 90% confidence, where my margin of error is 0.6. My best guess is X bar is 15.7. So to bring it back to those claims that we often see made, look, the claim might read something as simple as the average, we did a study, a 90% confidence produced an interval where we believe the average student will spend 15.7 hours studying, at least, again, on average. But that number might be inflated. The actual population mean might be 15.1, maybe 15.2. This number also might be deflated. It might actually be more than that. But again, it's a claim, so we'll take it with a grain of salt, not only the wiggle room, but also the level of confidence that it's projected in. In fact, to that end, when we write these assertions or these interpretations, we should always include those two ingredients. Look, what was the level of confidence? And also, what is the actual interval? Instead of simply making a bold claim as to, look, we talked to 250 students, and out of the whole school, the average is going to be 15.7 hours. Instead, we need to make sure we include these two ingredients. And I'll write my example like this. With 90% confidence, we claim that students will spend, on average, between 15.1 hours per week to 16.3 hours per week studying. We're not sure exactly what the average is, but I can tell you it's somewhere inside of that range, and that's the claim that we're making. In fact, I'm making that window, that interval, with this caveat. That's why I'll lead the sentence with it. 90% confidence that in fact there is. It's a 10% chance, so not very likely, but that interval I'm giving you does not contain the mean. And so people could take that with as much grain of the salt they want to, but certainly they are well informed with that interpretation. Let's actually look at extracting information from these confidence intervals. For the first one, a 95% confidence interval for the population mean time in minutes students take to complete a homework assignment is given in this interval. Let's say 28 minutes on the low end and 35 on the large end. What I want to do, I want to find some ingredients, is what is the margin of error used to construct this confidence interval? I have a picture up above to kind of help you out with this one. But what I want to do is I want to show you two ways to find the margin of error. The first one is a bit roundabout, and the second one's much more direct. But that formula is a bit of a cheat, so I want to start you off with the first one. So per this little picture, I see my margins of error hanging out here. Again, minus my margin of error, plus my margin of error. If I knew what the middle was, well, then I could pretty quickly calculate what the error is, because then I would just look at the difference between maybe the right and the middle, or the middle and the left. And so that'll be my first step, is I'll figure out what is the middle of the interval. In this case, since this is a population mean, the middle would be the sample mean. So I'll write X bar for that. This is equal to. If you want to find the middle between 2 points, we can do that. It's just adding these two up, 35 divided by 28, and dividing that number by 2, and that'll get us the actual middle between those two values. So I can do that. 28 plus 35 is going to be 63 divided by 2. 63 divided by 2 is going to be an okay number at 31.5, little decimal, but we can handle it. And this is the middle. This is the mean, 31.5. That was the middle that built how to construct that interval. But now once I know that, now there are lots of ways I can find the swing or the margin of error. I'll write my little epsilon backwards 3 character here. This is going to be equal to, have it as 35 minus 31.5. And we can evaluate that as simply 3.5. And there's my margin of error, the swing that got me there. And again, if I added that or subtracted it to my 31.5, I'd end up with my 2 endpoints. So that's the answer that we're looking for. Find the middle, find the swing. There's actually a faster way, and it actually looks really similar to this first formula, which is why I will circle this one, because that's a good one to know, add them and divide to find the middle. There's also a nicer one to find the, I'll write it clearly here, margin of error. And it looks like this. E is equal to, it's going to be a fraction. That's the only hint I'll give you, and then we'll actually get into it. If I zoom in on an interval, I have 35 to 28. The distance between those two, I can subtract them, would be 7. Notice the distance, if I look at this in more of a geometry approach, is 7. That was 1, 2 epsilons. So I have 2 epsilons is the total distance between those two. And so the formula, if I want to think about this, 2 epsilons is equal to the distance, or I can write it as 35 minus 28, which will give me the distance, divided by 2 epsilons, and that'll give me the solitary one on its own. So again, the math is going to be 35 divided by 8 is 7, divided by 2, and look at that, we get the same answer, 3.5 for my margin of error. So 2 ways to do it, but I think it's important to start with the first one because that's kind of the typical way, especially if you have the middle. It's much easier to simply to subtract. But if you don't, you can subtract and divide by 2, and you'll get your margin of error. So these are the two nice formulas for extracting the information, the middle and the margin of error. Let's say later that year, you discover that the true population mean was 37 minutes. In retrospect, was our confidence interval accurate in its inference? Circle and briefly justify your response. Was it accurate or maybe not? Well, again, our interval claimed that the population mean, again, the time, was somewhere in this interval, 28 to 35. And so it's like we're broadcasting that, hey, look, this is how much you should prepare to complete this assignment. This is how much time you should set aside. Versus in actuality, the mean was equal to 37. Bummer. Look at that. Outside of my interval. So really, the interval that we presented everybody with was completely wrong. It did not contain the mean whatsoever. Were we accurate in our inference? No, we were not. But what's interesting to point out is actually, we accounted for this. To be fair, we were very transparent. We said we were 95% confidence. So really, if we were going to put percentages on it, I was 95% confident when I gave you that interval. But of course, there was a 5% chance that the interval that we were giving was completely bunk, did not contain a mean. And unfortunately for us, we're in that 5% camp for this one. So again, confidence intervals are great. They give us good projections, but they can be wrong. And certainly there's a probability associated with it. All right, here's our last example. We have a mobile game. Melvor Idle is an idle RPG game based on the 13th most popular MMO game, RuneScape, sometimes referred to as RS3. MMO, for any of the uninitiated, stands for Massive Multiplayer Online Game. A 95% confidence interval for the population proportion of Melvor gamers who don't play RS3 is this proportion, anywhere between 71% to 85%. So again, those are the people playing the mobile game, but not the game that it was based on, the much bigger game, RuneScape. And so ideally, well, I'll get into the examples. Let me first get into the first step. Find the sample proportion p hat used to construct the confidence interval. Again, if we're talking about proportions, these should be relatively close. The sample proportion is what gives the population portion. These should be pretty close. This always refers to as the middle, or sometimes referred to as the point estimate. And that's what my little picture here shows. 85, 71 p hats in the middle. Again, if you like, there's a friendly formula for this. I just add the two up. In this case, it's 0.85 plus 0.71 and divide by 2. Again, to find the exact middle. Here we go. 0.85 plus 0.71 should give you a nice number like 0.156, still divided by 2. And so as a proportion, when I divide that, I should end up with 78 or 0.78. That's the answer that we're looking for over here. All right, it's 0.78, but certainly maybe it's more friendly to think about that as 78%. So that's the sample proportion. Again, I know it's anecdotal, but that's the sample proportion that built that confidence interval up above. So here's how we can apply this confidence interval, and we have two little applications here. The first one. For the last 30 days, Steam, a popular digital distribution of games, reports that there are 4,096 active players of Melvor. So RS3's marketing team is like, hey, maybe we can try to put an ad, pay for an ad, and try to capture some of those people who kind of are already familiar with our gameplay, and they might want to play our game. but they want to estimate the highest number of Melvor gamers who don't play their RS3 game. So the question is, what proportion should they use if they're interested in the highest estimate? Well, again, the actual estimate, the population proportion, is anywhere between 71% all the way to 85%. Again, 71 being the low, 85 being the high. Okay, I think we got this one. 85% on the high end. And so how can we put these two things together? With a 95% confidence, what is the highest number of Melvor gamers who don't play RS3, at least in these last 30 days? I have a number of people that play, and I also have a proportion that don't play RS3. If I multiply these together, I'll get the exact number of people I'm interested in. So it's going to be 4,096 times my highest proportion I could imagine, 0.85. If you multiply those two, you should get 3,481.6. You might be tempted to leave the answer there. Please do not, because we can't somehow advertise to 0.6 of a person. We'll make sure to round that number up, and we should get 3,482. And this is the number of gamers that we're interested in. And so again, you might look at these confidence intervals, and maybe some of them are bunk. They don't mean too much. But for the marketing team, it's important that they know how much they're investing, because maybe they invest some money, they put some ads out, and they get, let's say, 400 people to play their game. Well, then they can generate a proportion, an effectiveness of their ad. And then maybe on a later date, they can put another ad forward and see how many more gamers they can kind of pull forward to play their game. And they can understand their capture, if you will. And so statistics, particularly confidence intervals, are all over the place, where we take sample information, anecdotal, and we project it onto a population. These confidence intervals are our best guesses. We saw sometimes they're accurate and they give us good information that turns out to be true in the end, and sometimes they're not. And so it's important to understand these two important ingredients, and this is how we'll wrap. We have our level of confidence, this 95, this 80, and that tells you, again, that there's a chance that your interval is meaningless, that does not contain the population information you're interested in, but it should be pretty high. Additionally, we should understand that whenever we read these claims about population, the 2.5 hours, the 26% that we saw in the beginning, that these are claims being made, but these are not exact. In fact, there's wiggle room with them. So again, it could be lower, it could be higher. In fact, it's all equally likely to occur. But also, there's a chance that those claims are meaningless, that they are wrong. And that's why it's very important to also know the level of confidence as well, and take these educated guesses for what they are. They're educated best guesses. All right, let me end with this. If you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.